Alright, so here's our review for chapters 1 through 3. So we just start off with our sets of numbers. We have the natural counting numbers, which are what you learn to count with, 1, 2, 3, all the positive integers, and then we have the whole numbers, which is just the addition of 0. The integers are our negatives as well as our positive whole numbers. Our rationals are our fractions. So the integers, where we have a denominator 1, and the fractions. Our irrational are our square roots. Root 4 is not an irrational number because it simplifies, it's a perfect square. The real numbers are the rationals and the irrationals combined. And then the imaginary, where we have our square root of a negative number, which we define as I. If we're solving an absolute value equation, we need to keep in mind that, for example, the absolute value of 5 and negative 5 give the same result. So we're going to get two equations here. We look at the equation and then the opposite of that, the negative side of it. So I drop my absolute values to get the first one, and I get that x minus 1 is 4, x, and the second one is I take the opposite of that, x minus 1 is negative 4. I solve both of those, get x is 5, and get x is negative 3. So I was to plug those back in there. 5 minus 1 is 4, absolute value of 4 is 4, 7 minus 4 is 3, that one works. The next one, negative 3 minus 1 is negative 4, absolute value is positive 4, 7 minus 4 is 3. So they both work. An inequality is a little bit trickier in that we do the same thing where we get an absolute value on one side. To get our first equation, we just drop the absolute value. Another one is we take the opposite of it. So the opposite of that number would give the same absolute value. So the first one gives us x is greater than 2, and then when I divide by the negative on the second equation, I flip my inequality around. So instead of greater than, it becomes less than, and I get x is less than 0. So if I was to graph it, I have 0 going to the left, and then 2 going to the right, and so that is going to be or. X is less than 0, or x is greater than 2. So that's really it from chapter 1. If we jump into chapter 2, we started talking about functions. And the real thing about a function is that I put one thing in, I get one thing out. It can be the same thing out every time, but the key is that one input doesn't give multiple outputs. So if I look at the first one, we have this mapping of the domain, which is on the left side, and then the range, which is on the right side. So again, here's our domain, and then it maps to the range. This is my domain, it maps to the range here. And as I can see, 0 goes to negative 2 and 0 goes to negative 1. So that's not going to be a function, right? I have a mapping where one input goes to multiple outputs, so that's not a function. The next one, if I look at it, 5 goes to negative 8. 6 also goes to negative 8, but 5 doesn't go to anything else, so that's going to be alright. That is going to be a function. So the key thing, one thing in, one thing out. Alright. We can translate that into our what's called our vertical line test. So if I draw any vertical line on this function, I'm not going to hit it more than once. So that is going to be a function. Whereas composed to the next one, if I draw a vertical line, I can see that at these 2 points, I am getting multiple outputs for one input. So that's not a function. Alright, we then jumped into kind of a review of algebra where we're graphing these things. So I get it into slope-intercept form. I get the y by itself, I divide by negative 3. And then y equals mx plus b is my slope-intercept form. This is the m, this is the b. So the slope of negative 2 goes over here. And when I wrote this originally, I've lost my negative sign. So let me add it back in here on my presentation. So slope is negative 2. So that means my rise is negative 2, my run is 1. And my intercept is negative 6. It means that b is negative 6. And that means I go through the point 0, negative 6. So if I was to graph this, there's my y-intercept. And then I have a slope of negative 2, which if I was to just kind of sketch that out, if I was to put another point on first, be somewhere over there, somewhere right there, and just roughly draw a line through it, would look like that. So that would be my slope of my line. So again, you want to be careful you don't lose a negative sign as you go through this. Alright, let's look at the next one. And that's how when I lost my negative sign, that was the graph that I'd gotten before, so which is not correct. Okay. Let me back it up again. Sorry. Alright. If I am graphing, it's often easiest to find the x and y intercepts. The x-intercept is where I have a 0 for the y value, so I plug in 0 for y, figure out x, I get -4, so the x-intercept is -4, 0. For the next one, my y-intercept, that's x is 0, I plug in 0 for x, and I solve for y, and I get the 0.06. So those are my intercepts, and those are often going to be the easiest thing to graph, because if I was to just throw a graph on there, there's my axes. The intercepts are simple because they're just points on the axes, and then I connect the dots and I get a quick sketch of what my line looks like. For the next one, if I'm given 2 points, what I want to do is I want to use those points and I want to figure out the slope. So the slope is y2 minus y1, which is the rise. So there's 15 and 11. And then I have, you have to go the same order, a -6 minus a -12. Now when I did this originally, I was being quick and I lost my -12. So when I subtract a -12, it becomes +12. And if I simplify that, I originally thought I had that without my negative sign, but if I was to adjust it, you'll see in a second, I had it screwed up. It should be 2/3. And so that is my equation where I get y minus 15 equals 2/3 quantity x plus 6. And I could manipulate it from there, but that's just as good as any other equation form of a line. So you can leave it like that. You could test a point. If you put back in your original values of -6, you should get out 15. If you put in -12, you should get out 11 when you plug that into this equation down here. Alright, in terms of transformations, we have a parent graph, which is the untransformed absolute value, which is a vertex at 0, 0. And I start looking at transformations within that graph. So if I look at the -3 within the function, the +1 and the -2 multiplying, those all do something to it. That 3 moves it 3 to the right. The +1 moves it 1 up. So my vertex, instead of going 0, 0, moves to 3 to the right, and then up 1 becomes 3, 1. The slopes is what deals with this -2 over here. So that will, instead of being a 1-to-1 slope, so instead of doing 0, 0 and going up 1 to 1 like that, this thing has moved over 1, 2, 3 and up 1. There's the vertex, and it's steeper. It goes up at a slope of -2. So it actually goes down at a slope of -2. So if I was to graph it, there's my vertex, and those are my slopes. Alright, chapter 3, we started looking at systems of equations. So systems of equations are 2 or more equations, and we have different things that can happen. When we're looking for solutions to a system, we're looking for points of intersection. So we can see if I have parallel lines, there's no solution, there's no point that they have in common. Whereas if I have one line, and I imagine overlapping lines, they have multiple infinite points in common, so there's infinite solutions, it's the same line. And we use this idea for 3 points, or 3 variables. We're actually looking at planes of intersection. So 2 variables is lines, 3 variables is planes. And so different things can happen, but same general idea. So for this system of equations down here, what we're going to try to do is, instead of having 3 variables and 3 equations, eliminate something and get down to 2 variables and 2 equations. So I always label my my equations so I know what I've used. If I just add 1 and 3, so the first and the third, then the y's drop out. I have a plus y and a minus y, they go away. I'm left with this equation. And so I have something without y, and I want to do that again. I want to use it to get rid of using this equation. So if I do 2 times 1 will give me 2y, and if I have a -2y here, those are going to go away and give me another equation with just x and z. And then it just worked out this way, but since I have a -2z and a +2z, when I add these two, those will cancel. And just to note that we need to get rid of the same variable both times. If I got rid of y one time and z another, that's not going to get me anywhere. But I add these up, and I get something with just x. So x has to equal 5, and now I use that to figure out what z is. So I plug in 5 for x, and I figure out that z is going to be -1, and then I plug in 5 for x and -1 for z to figure out what y is. And I picked the first equation because it's the simplest, and I get that y has to be equal to 3. So that should work in all the equations. I can go back and check them, but that's how I solve a system of 3 variables. Alright, similar idea in terms of graphing inequalities. I graph the line where it's equal to it if it's less than. So in this case where I just have y is greater than, there's no equal to, I get a dashed line here, and then these values go up. If I'm worried about it, I put in a test point. 0, 0 is usually good. Is 0 greater than -2? It is, so it shades up this way. I graph the other ones, and I do my shading. Where they all overlap, that little triangle in black is called our feasible region. That is the solution to the system of inequality. So any point that lies in that triangle is going to work for all of those. We use that for linear programming problems. So linear programming problems sound big and scary, but you start by defining your variables. So we're given a bicycle store, 2 types of bikes. And I define my variables as the number of each type of bike, and then I need to figure out my constraints. So my constraints, first off, I can't have negative bicycles, so those are easy ones. They both have to be greater than 0, and we could kind of see that from just, we're given a hint here with this quadrant. We're only looking at the positive values in this quadrant. The third one, if I look at 30 entry-level bikes is what the store will hold, which means if I add up M and C, I have to be less than or equal to 30. I know I have $8,000 in inventory, and I'm given what they each cost. And so 300M plus 200C is less than or equal to 8,000. And since it's easy to work with smaller numbers, and I just have multiple zeros on both sides, I divide those out, and I get 3M plus 2C is less than or equal to 80. So those are my constraints, and now I graph them. And it's going to be easiest to figure out the intercepts. So for that one, I get 30, 0, and 0, 30 as the intercepts, and it's going to shade down from there. This one is a little bit trickier, but I still, again, figure out my intercepts, which means I set each variable equal to 0. So I get 0, 40 when M is 0, C is 40, and I get 26 2/3 when C is 0. I plot those points, and then that piece in there is my feasible region. So what I need to do now is to figure out my vertices, the corner points of the feasible region. So that's the hardest one to find, because what I need to do is I need to solve equations 3 and 4. I need to find the point of intersection. Well, we use some elimination, and I can find that M is 20. Once I know that M is 20, I know that C is 10, because M and C have to equal 30. And the last piece is I have all the corner points. I need to have an objective function. That's what I'm trying to maximize. In this case, it's profit. So I know that I get $100 profit for the mountain bikes, and I get $75 profit for the cliff climbers. So profit is 100M plus 75C, and I plug in the corner points of my feasible region. So the 26, 0, that is my vertex right there. The next one is going to be up here at 0, 30, and then the last one is the one that we found algebraically of 2010. So I plug this into my profit function, and I find that I have the following profits. And it's pretty obvious that the biggest one is right there. So profit is maximized when I have 20 mountain monsters and 10 cliffhangers.